Okay, so we're having a project about the Columbia AI Agent Campus. And the author include Jen Feng. He's responsible for the backend and the RL part. Uh, I'm for the I'm judging them for the front end and the design part. Hayu is for the going to through the whole project. He's going to design the project, design the map for our Columbia Valley. So. Okay, we can go through our agenda. Our agenda precisely meet all the requirements, including the goal, the data interpretation, and also the methodology system results. We are also going to talk about the limitation, future research for our future project. Okay, our goal is pretty simple. We're trying to build a Columbia Valley, which is in English located, which included all the Columbia scene, the campus view, including the trees, the grass, including different buildings. And also our campus simulated based on the generative agent framework. Our agent also enable running the multiple agent simulations and also replays all the available. So you can go through the replay, go through the demo in the future slides, our UI analysis and demos in the future slides also. Um, Also our goal actually supported our project supported for the local LLM execution, including the Olama default, with remaining capable for the OpenAI NASA's APIs. Okay. Our novelty, our motivations. So this campus actually including we can see from the map, including the yours, the lower library, the Hamilton, and also the Potter library. We also included in 12 different agent, including the English, the bios, including the schedules, including the locations. Those are all designed by Haiyu. Yeah, he's actually designed a whole map, the colors for our campus. The UI part actually face-based. It can fix the constant top controls as a zoom charge, which means this map can be zoom big or small. It can be precisely see the what kind of agent doing when we play the demo. We also improved the conversation box. The conversation box actually precisely match the each agent what they're doing. And in the bottom, the personal bar, it can precisely navigate the each agent what they're doing through the demo. It's a scramble bar. Also, the agent it can be enlarged. I actually match the textures. I design all the agent. It's in a Halloween style. I actually run them in a one in simulations. I actually did the texture motivations. I make them more precisely and more pretty probably. The backend part for the LLM abstractions, the default part is the Olama chat. I use the Queen 3, this kind of chat model, to embed in the model BGM M3. And we can also switch to the OpenAI compatible provider with the API key with a URL. Um, Also, we included robustic. We in the reply UI part, we actually added more robustic part because the reply UI actually connected with the different files with a texture file with a picture file. If one of them are probably have the problem, we can directly find them, and we can fix up questions. Yeah. So next part, we're gonna go through the data. The data is pretty simple. We have before the training, which is the input data. So for the input data, we our model, uh, it's navigates through the generative agents, the data configuration JSON. My provider is also Llama. The chat model is Queen 3, as I taught before. The embedded model is BGM. It's a default model. And another model, like a replay, it can be found in the URL. precisely in here. After we play, our files are directly stored in a compressed file. It have two parts, which is movement and the simulations. In simulations, it can it's basically as a frame movement actions. The simulation part is a text of the states of the conversations. The core part of the data is actually for the system. It's stored under the results checkpoint, the names, including the checkpoints per agent. They have the directly separate memory data for each kind of agent. Okay, let's welcome Jianfeng to illustrate the next part, our technology and MAPPO part. Okay.
Okay, so yeah, so thanks for my teammates judging. In the following part, I'm going to go through the basic methodology, system workflow, result analysis, and future research of our project. And also the demo showcase would be like in the final slide. Okay, so let's look at our methodology. Firstly, we are using the PPO, the Possible Policy Optimizations, as our core algorithm. Yeah, I'm sure most of you have heard about it. It's a really popular reinforcement learning algorithm that widely used in the industry. The key idea here is that the PPO uses clipping mechanism to prevent the policy from changing between updates. This keeps the training stable and prevents it from going off the rails. However, in our project, we have to handle the multi-agents cases. So we have to modify and adapt it into this module as what we call the MAPPO, the multi-agents possible policy optimization, as you can see on the right side of the slides. The main idea is that not only each agent can make decisions based on only what it can assert locally, but also just share informations during the training process so they can learn to work together as a team, even though they're actually acting, they're owning just using their local informations. Okay, next page. Thank you. Yeah, so let's okay, so here is this basically our important functions of our MAPPO implementations. So firstly, we have this state extractor. This pulls all the relevant informations from the each agents, like their personal, their current locations, their actions, their plans, and so on, which give us structural reinforcement learning state representations. And in addition to the action space, we define six actions types that the agents can take. For example, to continue what they are actually doing, wait, change locations, revise their scheduling, and skip reactions or something else. So this cover most of the behaviors we can see in the campus environments. Okay, so next, it's about like our reward functions. This is really important. So we use a multi objective reward with five main components, as you can see, like the personal consistency score and planning completion score, which help us ensure agents behave and to stay the true to their character. And finally, we have the trainer and policy network. This really handle our training loop. Yeah, and on the right, you can see that. Uh, okay, sorry. Yeah. And all right, you can see how these modules work together. The game environments fits into the MAPPO trainer map wrapper, then connects to the agent's decision layer. Agents can either make decisions purely or through a mixture of R and L decisions. Okay, next, please. Thank you. Yeah. Okay, sorry. Yeah, and this part is over like okay, so this part is gonna be like our big picture. This is our complete system workflow. Okay, so the whole system is mentally dividing the three phases. So as you can see in the picture, the phases one is initializations. We start by loading the configuration, setting up with the environments with the layout, something else. And phase two is actually the most important part, is the simulations loop. At each time step, every agents go through a decision process. They move around, they can just manage their schedule, they perceive the environments, they make plans. And meanwhile, our Llama model, the LLM inference pipeline is actually working, retrieving the relevant memories, informations, constructing the prompts, getting responses from the LLM, and also updating the agent's memory. And while all this is happening, our R system is actually collecting the data. We extract the agent state, record the actions, compute the reward scores based on the five rewards as we said in the previous slides. For example, the personal consistency, the interactions quality, store all the these transactions. And when we hit the training interval, the MAPPO trainer processes all the relevant buffers and finally updates both the policy and the value networks. And finally, the phase three gives us like the evaluations, metrics, and outputs. So, for example, some kind of a JSON file for our future simulations loop or something else. So basically, this is our complete end-to-end pipeline of our system. Okay, next, please. Okay, so let's look at the results analysis part. So basically, we compare our version stat against the baseline across five key metrics and dimensions you can see here. So as you can see in the radar chart, our reinforcement learning versions, the blue area, just greatly outperforms the baseline in almost every app set. So the most dramatic improvement is actually in the directional quality, which is nearly 4 times better than the baseline. And the bar chart shows the over scores our versions achieve nearly like a 7.85 out of a 10 compared to just like 3.6 for the baseline. So, they're just more than double improvements. Okay, next, please. Yeah, and now let's look at the reward dynamics stuff. This kind of a chart shows how our three agents learn over like 100 steps. So the right side you can see which shows the trends of the rewards. It's actually and especially interesting. We see three different learning patterns. Agent one has impressive changes with the overall update trend, and agent two has a big spikes, in rewards that at the beginning before they level out. And Agent 3 has a gradual convergence process with the reward dropping from the high level and then just fall back down. And this different learning curve show each agent use a different strategy or different like policy to improve their behavior in the simulations environment during the reinforcement learning training process. Okay, next, please. Yeah, and here is just the training stuff. Again, the left panel, the left figure just display the training losses for our three agents. We can see that the policy losses, the value losses, the entry point losses are changing different weights of the agents. And agent three, on the other hand, shows a big, decline in value loss early in training, which means the early the learn just quickly. But the agents one agent just on the other hand just shows a more gradual improvements. The learning curves also displaying that the total returns per episode are located in the right figures. Agent 1 shows a lot of variations with the positive trend, which suggests that she is actually exploring. And Agent 2 performance stays pretty steady with only like small changes and modifications. And Agent 3's numbers going down clearly at first, but then just fall down back, which means that the policy is becoming more and more stable. Okay, next, please. Okay, so here's our limitations and future research part. We actually have the main limitations. So firstly, we have limited training iterations as we said in previous slide. We just only have the 100 steps. So uh, so our agents might not, have fully convergent yet. So maybe in the future we could just multiply the number of the steps to maybe, for example, the 500, 1,000 steps or something else. And secondly, our action space is actually simplified to just, 6 types, which might not, cover all the realistic motions or behaviors in the campus environments. And thirdly, the reward functions need to be like fine-tuning because our current balance of our five components might not be optimal. So for future research, we have the three key dimensions. and directions. So firstly, just refining the reward functions for ensuring all of the agents, for example, 12 agents behave more consistency over time. And secondly, we need to like expand to include more agents for much more complex environment simulations of the environments. And thirdly, improving our state representations to better capture agents' long-term goals and planning is really important. Okay, so the next page is yeah, so next page is gonna be our demo showcase. Yeah, actually the demo showcases show like our front end interface of simulations. We have three agents here, and we just could click into this button here. We could just zoom in, zoom out, following how it's the agents is doing and how they're actually plan to do. And the history would be like recorded in the upper section of the chat box here. Okay. Yeah, this almostly an hour project. So if you are interested, you could just refer our report and our ECS 6893 web page for more information. Thank you.